We have two strings, and we want to get the length of their longest common subsequence. If there's no common subsequence, we're going to return 0. Now, a subsequence of a string is a new string generated from the old one, the original string, with some or none of the characters deleted, without changing the relative order of the remaining characters. So for example, we can get ACE by removing B and D from this string here, right? And it's different. We can't get AEC because E never ever comes before C, okay? And now, another instance that I think is useful, is educative with the color coding, right? Let's make this as big as possible. So found and cloud, for instance, here, right? The longest length common substring between the two of them is 3, because if we remove C and L, we have OUD, and F and N, we have OUD between them. Same with this, BED, IEAD, remove B here, remove R and A here, we have these. And here, there are no common strings between them, between bed and hall. And so you can think of the problem like drawing non-crossing lines between those strings, lines that don't cross, because if they cross, it means we swap the order. So non-crossing lines between both strings. And when we look at the solution to this problem, right, we're gonna use two cursors to point to characters in string 1 and string 2 respectively, and the cursors are I and J. Now, when there's a match between what I and J are pointing to, we can think of that as a line that connects the two of them. And so the trick to this problem is breaking this into subproblems. And what was the subproblem here? Each string is made up of suffixes. So D is a suffix of BED. ED is a suffix of BED. And so we're going to look for a sequence of non-crossing lines starting from the smallest line, right? I mean, building up, actually, not necessarily starting, as you'll see shortly, building up from the smallest prefixes of these two strings, okay? And we'll get to this table in a second, but it's a standard part of dynamic programming problems if you've been following along. So we start off with I and J at 0 at the beginning, pointing to the first characters of this string, and that's what this here represents. And so we're initializing this table that is going to be used later on. But what we're trying to do now is, in each step, we're going to check, is there a line connecting what I and J is pointing to? And depending on whether there is, we're going to do a variety of different things. If there is, right, we are going to, I think it's useful to see this in code at this point. If there is, and I'm going to show the full thing, the full part of this code, but let me just highlight something. So if they match, actually, I think it's too early. Ignore that. If they match, we're going to do something. If they don't match, we're going to do something. Okay? Just keep that in mind. If what I and J point to match, we're going to do something. If they don't, we're going to do something else. Okay? And what is that? What are we going to do? Well, if they don't match, as you see here in this case, we are going to move I forward. And what does that represent? And that represents dropping off B and only considering this suffix ed. Now remember, the solution to this problem relies on building things up from the smallest suffix up into the whole word. So we're getting there. We're not there yet. And so that's why this moved forward, right? Because I moved over here. I became 1. J is still at 0. Then we check again. You can see there's still no match. So we move forward. There's still no match. So we move forward. And now I is pointing to an empty string. So now the suffix has moved from BED to ED to D to nothing. And when you looking for the common subsequence between nothing and something, you get nothing. So this is gonna give us 0, right? This represents 0 over here. And so we can, there's no line connecting, right? Nothing. And if J is at this and I is here, pointing at a string of nothing, there's no line connecting it. And so we've checked that. up next, we are going to look at the code for this, okay? And now some things might not make sense in the forward pass, but if you hold on to the end of the video, like, you should be able to draw the connections and see the whole picture. And so we have this function, we're passing in the two strings, we get the lengths of the both of them, and the lengths of the both of them are useful because they help us create this lookup table that, again, is very popular in dynamic programming. And then we get to this call function, this helper, passing in both strings, the first positions of I and j respectively, and the lookup table. Okay, so now the focus is on here. And so you just witnessed I being equal to the string length, right? Basically, which is when it was pointing at nothing, right? And if it points at nothing, for this combination that we've explored, we're going to return 0. There's no line connecting the both of them, right, at that point. However, what was happening and how was I being moved, right? Because in the beginning, when we started off with 0, 0, right, and this function came in here, right, with 0, string 1, string 2, I of j of 0, and a lookup table, we came in here, dp and I and j is still -1, because that's what we set everything to here, -1. So, and the strings didn't match. There was no connecting line between the two of them. So this else block was evaluated. And what does this else block do? It's checking, okay, which is bigger? If we leave that whatever I is pointing to behind, we cut it off, or if we leave whatever j is pointing to behind. So the reason this moves left to the left, I is just moving forward, is because this branch here is being called every single time this function is recursively called here first. Okay, first. And so when we are done, basically when I starts to point to nothing, I will return 0 over here, right? It cascades back and now evaluates this second branch where we're evaluating, well, what happens if we move j instead. So that's exactly what happened here. And so j finally moves. We're evaluating what j is because we're going to check which is bigger. Right? Again, we're looking for the longest. If we're looking for the shortest, then we would minify this, right? But we're looking for the biggest, so we check for the maximum value. And again, this pattern is a common dynamic programming pattern. If you've seen the knapsack problem, right? The recursive version of the knapsack problem, where, okay, we're evaluating if we take this, if we don't take what I is pointing to, and then we're evaluating, okay, if we don't take what j is pointing to in this case, I'm looking for the max between the two of them. Hence this branching that you see here in this recursive tree. So this calls itself again, and you notice that if it calls, then it's gonna still end up coming back here to this left branch, and then so this branches to the left where you'll be incrementing I once again and getting 0, right? And then going back and calling what's at the right one more time, right? I'm looking for the max between the two. So this is 0, and then what does this give us? DNA, nothing. Call it again. Now I is at 3. It's pointing to nothing, so it's going to backtrack again and come to the right. So that's what's represented by this line here, represents that branching that we've seen up until now. And so 2 and 3, in this case, what do you have here? We can draw a line between the two of them, between what I is pointing to and what j is pointing to, because they're the same. And so finally, we come into a case where this is true. And so what does that represent? It means we're saying, okay, add 1. And notice how now we're evaluating the smallest unit of both words. We finally got into the point where we're evaluating the smallest unit of both words, which is d and d, right? It's the smallest suffix for both words. And so we're going to record that as a line, and that's represented by the 1 you see here, plus shift both I and j this time, right? Not just one or the other. both I and j, what they point to by 1, and which leads to something empty, and that causes the 0 to trigger here, so this evaluates to 0, and then finally we set something in dpi and j, and we set that to be 1. And semantically, what that represents is if we were just evaluating the suffix of made by 3, 2, so 3 here, just the string here and here, what is the longest common subsequence? And that is what 1 is. And so now, as we backtrack, we've returned 1 here. So this is going to evaluate to 1. So finding a max of 0 and 1 is going to be 1. So everything here is going to populate to be 1. And what does that mean? Semantically, it means if we are just evaluating this suffix and everything in here, the longest common subsequence would be 1, would be just 1. That's what this means semantically. And then we keep going up the call stack till we get to this point early in the game where we had just chopped off B, and we're building up the solution to E and D. So for the solution to E and D, it's not enough to just consider if I moved forward, cursor at I moved forward. We're also going to check the next thing, right, which is this branch over here, if J moved forward. Okay, and so we remember we have the solution to D, right? Everything is 1. So now we're checking E and D, right? We're using the solution of D to find the solution of E and D here. Okay, so we have 1, 1. And in this case, 1, 1, E and D match. Look at that. E and D actually match. So there's a line connecting what's here. So we're going to do what we did in this case, in the case of D and D, where we, add 1, which represents that one line, because we came here, right? Call it again by moving both forward, right? And when we move both forward, 1 and 1, we get 2 and 2, and we've seen 2 and 2 before, right? We know the solution to that is 1. So instead of having to come here and now start evaluating these again, we just take the solution that we found from this lookup table, add 1 to it, and in this case that answer is 2. Yeah, so that means for E and D and this whole thing, the longest common subsequence is 2, and then we go back up, right? For E and D and READ, it's 2. That's what this means. And we're back to the top where it all began, right? With I and J 0. And so this started off by calling the left-hand side of this. So this math of max is still pending. So it's going to do the same thing for the right-hand side. Call itself again. And you can see how, for instance, in this case, right, it just called itself once. B and E don't match. It's gonna move I this time, right? And then E and E match again. But we found the solution before. So instead of having to compute a ton of different things, we just pull the answer from the lookup table, which is 2, and move it up. And we just keep going till we're done. Same procedure, because we've explored all the branches of this problem, right? So there's not much else to do. The algorithm just keeps going, keeps finding what's out there, and the semantics carry forward, right, of what each of these mean, till we fill out what's here, which represents, if we considered the whole of both strings. Okay, now the solution, and we return that, right, dp I and j, because originally, right, the first recursive call I and j is 0, so this is going to end up returning 0 anyway. Okay, because notice we don't we only ever return stuff in the branch in this like terminating condition where I and J or J move to the end. But originally, right, in the very first call, I and J was 0. So everything here had to finish before you wind up here. Okay. And that's that about that. So time complexity is n by n, O of n by n, right? That's the explanation, and the space complexity is O of n by m. I hope that makes sense. Hard problem, in my opinion. They say medium. I think this is a hard. So the trick is, again, building sub-solutions with suffixes and just letting things go on, keeping track of a 1 whenever we have a connecting line between what I and J point to, considering if we skip that, what I is pointing to, and if we skip what J is pointing to, which is bigger, and moving both I and J whenever we find a line connecting them, the two of them. So considering the suffix without what they're both pointing to, as you see here, and then using the lookup table to save computation by skipping this branch completely if we've said something in there and just returning it down here instead. Okay, that's all there is to it. Cheers.